We're going to look at energy changes. Just be aware as we go through this, the content in green you could be assessed on, while if your exam is highlighted in grey, this will be content that you will not be assessed on. It's not in your specification. Content for everyone in all sciences is the idea that we've got this idea of conservation of energy. This is the idea that the amount of energy that goes into a chemical reaction must come out. So it's linked to that idea in physics that energy cannot be created or destroyed. Now, usually in a chemical reaction, we do observe a temperature change. Some reactions will release energy while others take it in. And that's the predominant huge part of this topic. Exothermic reactions are ones that transfer energy into the surroundings. So with this, we're normally going to observe a temperature increase and surroundings will warm up. There are loads of different examples of these. Combustion, so burning is an example. Neutralization reactions, so the reaction between acids and alkalis is another example. Displacement reactions are also exothermic, as are oxidation reactions. So there's loads of different examples. The way this might be assessed is you might be asked what kind of reaction a neutralization reaction is, and that will then be prompting you to say either, well, in this case, exothermic. We do have some uses, and the important thing here is just to be aware of them because it might be a context they give in the science exam. We can use it for self-heating cans, to example, heat up food. They can also be used in injury packs as well as hand warmers. Endothermic reactions now are reactions that take in energy from the surroundings. Typically, what this means is the surroundings cool down and we'll observe a temperature decrease if we're measuring the temperature. Now, examples of endothermic reactions involve salts dissolving in water. It's a link to your chemical changes topic. It also includes thermal decompositions. Now, here, typical traits to help us identify its thermal decomposition is look for normally one molecule been heated and breaking down to form a couple of different molecules. And also the reaction between citric acid and sodium hydrogen carbonate is another example. For endothermic reactions, again, it's more important to just be aware in case they throw a bit of an odd context at you. We do use these in sports injury cold packs as well. Now, the way that we can really tell if reactions endothermic or exothermic is fundamentally going to come from, during that reaction, what are we seeing observe, or what are we observing happen to temperature? So the best way of doing this is to record your start temperature, add the reactants together, and record the biggest change that you see. This might be the highest temperature or lowest temperature. If the temperature increases, the reaction must be exothermic, while if the temperature decreases, the reaction must be endothermic. You can also start to try and figure out the order of reactivity of elements by using these reactions. So we can place these in order by their observations of what we see happening with water and dilute acids. But what we can also do is we can add them and not just look at how much bubbling we see, but also try and measure temperature. So if we add a fixed mass of metal to a fixed volume of acid, we'll record the biggest temperature change that we see, and we'll do this with different metals. The bigger the temperature change is, the more reactive that substance is. We'll discuss the required practical around this at a later point, but for now, be aware that we can investigate different reactions and energy changes. And the basic setup is we'll have a polystyrene cup that we use because it's a really good insulator. And within this, we'll have our reactants added together. And we'll normally have a lid, again, to reduce heat loss or reduce energy change, and a thermometer through the center. So we use that polystyrene cup to reduce the energy transfers. We've added our acids, normally the liquid, record our start temperature, then add your other reactant. Add the lid, stir the solution, and we'll record the highest or lowest temperature that you see. That'll be recorded as our temperature change, and then we'll repeat this 2 more times to find outliers, calculate average. And then if we're maybe investigating the effect of adding like a different mass of metal, you then repeat this all again with some different masses of metal and see what the relationship was. Or in this case, 4 different test solutions, so maybe different acids. We're going to have a look at reaction profiles, but as a key phrase to be aware of going into this, we've got this idea of activation energy, and this is the minimum amount of energy that particles need to react. So you'll later learn about the collision theory and the idea that for particles to react, they need to collide with enough energy. Activation energy is the energy that's required for these particles to react in the event that they do collide. So we need these both 2 conditions to be met, a collision to occur with enough energy. Be prepared in your exam to construct reaction profile graphs, and you might have to draw this for either an endothermic reaction or exothermic. Sometimes as well they might ask you, for example, to label axes as well. But the purpose of these is they're showing the overall energy change that reactions got. Be really systematic if you're asked to construct a reaction profile from scratch, because this could be a potential 3 marks. Draw a labelled axis. Now we tend to have reaction progress along the bottom and potential energy up the side. Now this is going to be an exothermic reaction, so we add the potential energy for the reactants. If they give you the energy in and out, then make sure these match to your scale. If they don't, I would recommend go reactants halfway up the scale. And in this case, because it's exothermic, I'm going to step that down here for my product line. So this exothermic reaction, the products have less energy, so I've lowered the potential energy down. And this is all down to the fact that energy has been released into the surroundings. Once that's done, we'll then join these 2 with a hump, and the bottom of that reactant line to the top of the hump is known as the activation energy. If we look at this from the other way around, if we're asked to draw an endothermic reaction, we start in the same way. We've got a reaction progress along the bottom and our potential energy. We will then add our levels. So reactants, again, you could do the halfway point, but because this is endothermic, make sure it's definitely above your reactants. So in here, in an endothermic reaction, the products have more energy than what went in. This is because energy has now been gained and taken in from the surroundings. But again, we need to join these up with this raised hump. And notice we are still going from the bottom of the reactant line up to the top of the peak to label the activation energy. The energy change is the distance between the reactant line and the product. So whenever we draw those activation energies, it's always from the reactant up to the top of the peak. If we're drawing energy change, it's from the reactant and we point it down to the product or up to the product. By looking at these reaction profiles, we should be able to immediately identify if these are exothermic or endothermic. Endothermic should increase, while an exothermic should decrease. So we're drawing our activation, we go from the reactant line up to the top of the hump. While we're looking at our energy change, we're going to go from the reactant line to the product. On to higher content only. In any chemical reaction, what we tend to see is that we have our reactants come in, products come out. The atom number is exactly the same, but the way in which those atoms are bonded together are different. So in a chemical reaction, we break bonds and then make new ones. Now these are endothermic and exothermic processes. So to break any bond, energy has to be supplied. So actually, this process of bond breaking is endothermic. It has to take energy in from the surroundings. Now that's normally supplied by the activation energy, but it is endothermic. When we then form new bonds, this is an exothermic process. So energy is now released when the bonds in this product form. And this is the exothermic part. If we release more energy than we've taken in, that would be an exothermic reaction. So with this, in an endothermic reaction, what's happened is when we've broken those bonds, it has taken in way more energy to break those bonds than it released when new ones formed. So overall, it gained energy. During an exothermic reaction, the potential energy decreases. This is because the energy released when we've made new bonds was a lot higher than the energy that was taken in to break those bonds. So now the energy taken in to break those bonds was less than the energy given out, and so this is an exothermic reaction. Now also on higher, you might be asked to find the energy change that's occurred. So we need to start to find now the energy that was needed to break bonds and the energy released when we've made new ones. Now for this, the overall energy change is equal to the amount of energy needed to break bonds minus the amount of energy released when bonds were made. If we have a look at this equation, so you will normally be given a structure such as this and you'll be asked to use bond energies in a table provided to calculate the enthalpy change. Consider this the energy change for the reaction. For this, be really systematic around how you approach it. It's going to be about calculating the energy needed to break bonds. So for this, the first step is identify the bonds that you've got. So I've got 1 carbon double bond, I've got 4 carbon hydrogen bonds, and 1 bromine-bromine bond. So we've identified the bonds that we've got and the numbers of each, and then substitute in their values. So you'll have to use the table here. We've got 614 plus 4 lots of 413, so this bond here, plus 193. My bonds broken took 2,459 kilojoules to do so. Once we've found that, we now repeat this process, but now for the energy released when bonds were made. So we look at the bonds on the other side. We follow the same approach. How many carbon single bonds do I have? Just 1. I've now still got 4 carbon hydrogen bonds, so they're still there. But I've now got 2 carbon bromine bonds, which are here. We've identified our number of bonds, substitute in our values. Then go through and find the calculation. So in this case, the bonds made released 2,552 kilojoules. So our energy change is energy in minus the energy out. So bonds broken minus bonds made. So here, from our values that we previously calculated, we'd end up with 2,459 minus 2,552, giving me an energy change of minus 93. Minus numbers are fine. This just means end up with less energy. It's an exothermic reaction. If the energy is positive, it means the energy's gone up. That must be an endothermic reaction. So this reaction must be exothermic because the products have less energy. For separate science only, we're going to look at cells and batteries, which you can expect to be on your exam this year. Now, a simple cell is made by connecting 2 different metals and having them in contact with an electrolyte. So we need 2 different metals because these are going to work on the idea of different reactivities. So we've got electrolyte that's here, our first and our second metal. This will generate an electric current. Now, simple cells work by actually having a difference in reactivity of these substances that generates potential difference. The voltage that we generate depends on the type of electrode we've used and the difference in reactivity between them, as well as the electrolyte, and be prepared to answer that as a 2-mark question. But the bigger the difference is in reactivity, we're going to find the bigger the voltage produced. Batteries now consist of 2 or more cells that are connected in series, and the purpose of this is to provide a bigger and bigger voltage. You'll notice that these diagrams look quite similar, but there are some differences between them. So watch out if you are asked to draw a diagram of either a cell or electrolysis. Electrolysis will have 2 graphite electrodes typically, and they will have a power supply. However, in a cell, we will have now 2 electrodes and there'll be no power supply. actually this is generating the potential difference. So this is the power supply. So electrolysis is using an electric current to make a chemical reaction, while a cell is using a chemical reaction to generate an electric current. They are working in opposite ways. Non-rechargeable batteries tend to be alkaline batteries, and what basically happens is when the chemical reactions within that battery and within those cells stop, the reactants are used up, there is no longer a potential difference. That battery is then run out. However, in rechargeable batteries, what we can do is use electricity when we recharge that battery to reverse the chemical reaction that's taken place, and in doing so, it then means that when we remove that electrical power supply from the recharge away, the original reactants are back and then can react again to generate a potential difference. When the battery runs flat, we put it back into the power supply, it will reverse the chemical reaction and hopefully send us back to where we started. This leads us on to fuel cells. Now, these are supplied by an external source of fuel. So in this case, actually, hydrogen and air has been drawn into, particularly the oxygen we're after. And what we've got is the fuel been oxidized to produce this potential difference. When we look at hydrogen fuel cells, what we've got is the oxidation of hydrogen, so that's the fuel really going in to produce water. So the overall word equation for what's going on in this fuel cell is that hydrogen plus oxygen is making water. What's actually going on is a bit more complicated than this, and we'll have a look at that in a moment. But for now, hydrogen fuel cells are an alternative to using rechargeable cells and batteries that contain chemicals that are notoriously quite bad for the environment. So be prepared to explain how these work, and in particular to write some half equations of what's happening at the anode or the cathode. So at the negative electrode, what we've actually got going on is that hydrogen and hydroxide ions are making water plus electrons. What the positive electrode, we've got oxygen plus water and these 4 electrons making 4 hydroxide ions. My advice is have these on flashcards and learn them, because what they're going to ask you to do in your exam is to write the equation for what's happening at each of these electrodes, so have them prepared. Now, if we look at all the reactions happening, this is now the combination of both the reactions at the same time. But if we cancel out the common bits, so for example, notice the 4 electrons are on either side of the equation, the 4 hydroxide ions are on both sides too. If we cancel this down with the stuff that just is kind of left over on each side, the overall chemical equation is 2H2 plus O2 making 2 water molecules. You might be asked to evaluate the different types of cells. So alkaline batteries are cheaper, but they're ending up in landfill, and what we know is that they contain chemicals that are notoriously bad for the environment and can cause like buildup of toxins, for example. Now, rechargeable batteries will reduce the amount of having to go to landfill because in theory these can be recharged, so therefore reducing our use of resources. But they too tend to be more expensive, and we also, for recharging them using electricity, may be using crude oil to actually help with their recharge. Hydrogen fuel cells are easy to maintain, and what we're going to find is the only product is water, so we're not going to have here any harmful chemicals produced in any way. However, hydrogen fuel cells are expensive, we need hydrogen, which can be difficult to obtain, and hydrogen itself is also flammable, so it causes a safety concern around this.